Hello, AP Calculus students. Mr. Meunier here again. Today, I want to quickly run through topic 1.14, covering infinite limits. These are just limits that have solutions that are infinity. If you look at these two pictures here, we have the f function, 1 over x minus 1, and we also have a g function, 1 over x minus 1 squared. Each of these graphs have similar characteristics in that they are moving straight up or straight down at a certain value. And that value happens to be 1. And we can label what's happening within that with our limit notation. So if we quickly run through this exercise, which we should all be able to do, example 1a is saying, what's the limit as x approaches 1 from the left side of the f of x problem? Well, here's 1. The left side of 1, we can see that curve is falling straight down, which means the limit is negative infinity. Now the right side of 1 would be over here, and if my picture could have all of it together, that is rising straight up towards positive infinity. And then the limit as x approaches 1 over all would be the left and right sides coming together. And we can see those two pieces are not going to the same spot. Therefore, that does not exist, a DNE limit. Now on D here, the G graph. Again, this one was labeled G of X up top. Don't look at the F there. It is a G of X, and I'll just show you that again. G of X graph. The left side of 1 for the G of X graph here, there's 1, the left side's moving straight up towards positive infinity. The right side of 1 is also moving straight up towards positive infinity. And the limit as x approaches 1 over all is the left and right coming together. Two options on this we've discussed. Since both sides are going to infinity, we could say that, or we could say it does not exist, because technically infinity is not a value we can attain. Nothing new about that. The only new thing is what is happening in those curves at that spot of x equal to 1. I think we know, I think most of us would know, that there's a barrier going through there. And we tend to show that with a dashed line called an asymptote. There's a vertical asymptote occurring. So what do limits that produce results of infinity or negative infinity say about the function? They say there's a vertical asymptote at that value. So again, since we had infinities or negative infinities at that value of 1, that means there had to be a vertical asymptote occurring at that location. And that's a definition for vertical asymptotes. If your limit as x approaches a number from the left is infinity or negative infinity, or your limit as x approaches a number from the right side is infinity or negative infinity, then you have to have a vertical asymptote at that x equals c value. Well, how do we get that without necessarily looking at a picture, without maybe doing a limit every single time? Well, it kind of goes back to algebra class. Fractions are not good situations. The bottom of fraction cannot be 0. Again, denominator cannot equal 0. So where does that happen at? Where does the denominator equal 0? Well, take the denominator, put it equal to 0, and solve. Again, I always like to factor things. Factoring things is good. So for instance, x squared plus 1 does not factor. That's a sum of squares. Those do not factor. But x squared minus 1 does factor into x plus 1, x minus 1. Those two pieces cannot be 0. So we're going to say x plus 1 cannot be 0, x minus 1 cannot be 0. Therefore, x cannot be negative 1, x cannot be positive 1. Both of these would be vertical asymptotes. Vertical asymptote at x equals negative 1, and positive 1. They're vertical asymptotes because we could not cancel them out of the problems. It's a non-removable discontinuity from the last section, a non-removable discontinuity. We could not cancel this out of our particular function. Now, part B here, we want to factor. Again, always try to factor your fractions and see if you can cancel some things out. The numerator is a trinomial. We want to multiply to be -8 and add to be positive 2. Well, that's going to be an x plus 4, x minus 2, while the denominator, x squared minus 4, is a difference of perfect squares. That'll be x plus 2, x minus 2. When we work this out, the x minus 2 pieces cancel, giving us x plus 4, x plus 2. The x plus 2 in our denominator cannot be 0. X plus 2 cannot equal 0. Therefore, x cannot be -2. That is a vertical asymptote. This x plus 2 piece that we could not cancel out, it's non-removable. That piece cannot be 0, so x cannot, vertical asymptote, VA, at x equals -2. The other piece, the x minus 2 piece that we canceled, we talked about last class, that would produce a hole. That's a removable discontinuity. We canceled it out of the problem. A hole would be formed in its place. All right, so again, factors cancel, factor cancel. So again, same idea here. Fractions are not good. Fractions tend to lead to these asymptotes. Here, this x minus 1 piece, it's already been factored for us. That's not going to cancel out. X minus 1 cannot be 0. X cannot be 1. Vertical asymptote at x equals 1 is going on there. No good. Could not cancel it out. Cotangent does not look like a fraction. I think you have a problem like this similar in your continuity homework. That's a tangent. Well, cotangent is a fraction. It's actually the cosine over the sine. Cosine over sine. So we have to think to ourselves, when does sine, the sine function, the denominator, cannot be 0? Well, what are the values where sine equals 0? Well, from your chart quizzes with Mr. Gatens or unit circle quizzes, we need to kind of know that sine is the y value, and the y value equals 0 on that unit circle at the 0 degree or the 180 degree, which is 0 and pi in radians. So x cannot be 0, pi, 2 pi, etc. So there's a vertical asymptote at x equals, some way of writing this out. A lot of times people say at every pi k. Pi where k is an integer, like 1 pi, 2 pi, 3 pi, 4 pi. All right, so that's finding vertical asymptotes, finding vertical asymptotes. And finally, solving a limit. Ideally, if the limit problem, we plug 1 in. If I did that, I'm going to get 1 over 1 minus 1, which is 1 over 0. That's undefined. That doesn't have an answer for me. So it's not real useful. So what I kind of do on something like this, since it's not asking you to plug in 1 specifically, it wants the left side of 1. You think of a number line, 0, 1, 2. If I'm just to the left of 2, or 1, just left of 1, as close as I can possibly be, I'm at like 0.9 or 0.99 or 0.999. Basically, I'm going to plug in 0.9 repeating as close to 1 as possible. 0.9 repeating is what needs to happen. Since doing the shortcut and plugging in 1 didn't work, I need to actually plug in 0.9 repeating. So 1 over x minus 1 is going to be 1 over 0.9 repeating minus 1. Now, when that happens, again, if I have 0.9 here, 0.9 minus 1 is 0.1. 0.99 minus 1 is 0.01. 0.999 minus 1 is 0.0001. 0.9 repeating minus 1 is going to be, they're all negative. 0.99 repeating minus 1 is going to be a negative number. 0.000, a whole bunch of zeros and a 1. A whole bunch of zeros and a 1. That's a really, 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 really small number. And if you take 1, for instance, and divide it by negative 0.1, you get negative 10. If I have 1 and divided by negative 0.01, that's negative 100. 1 divided by negative 0.0001 is negative 1,000. Long story short, the smaller this gets, the bigger your solution is. If you divide by a super small number, you get infinities for an answer, super large numbers. So this is going to be negative infinity. So kind of an unwritten rule, integer divided by 0.00001 is going to equal some type of infinity. And this was a negative infinity because it was negative 0.0000001. So same kind of thing happens here on example B, where again, ideally, I'm going to plug 1 in. I know it's the right side of 1, but we usually just want to plug in the number. Here it's not going to work because 1 take away 1 is 0, and 1 over 0 is undefined. But if you look a little bit closer, this is actually plugging in just right of 1. And if I'm just right of 1, as close to 1 as possible, you're going to plug in 1.0000001 is what it comes into. 1 with a whole bunch of zeros and a 1 after it. So the limit as x approaches 1 from the right is 1 over 1.000 blah, 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 1 minus 1. Again, it's 1.000, a whole bunch of zeros. That's what the dot, dot, dot is. As many zeros as you can ever imagine. Throw a 1 on the end of it, and then subtract 1. If I take 1.000000001 and subtract 1, I'm going to get just a positive 0.000, whole bunch of zeros and a 1. And if I take a number and I divide by that super, super, super small number, that's always going to be infinity. An integer, any value divided by this super small number will tell you infinities. Now, if they asked us about 1 overall here, just kind of adding this on, limit as x approaches 1 over x minus 1, I couldn't plug in 1, so that means I have to do left and right. That's 1 over 1 minus 1, which is 1 over 0. Since that 1 over 0 happens, you need to test left and right, which is what we did. We tested left and right already. I have the negative infinity and the positive infinity. Those two pieces do not come together. They come to separate spots. So 1 over all would be a DNE, a DNE. All right, guys, I hope that made a little bit of sense. I'm happy to see some of you in class here. I'll see all of you here soon. Have a good one. Topic 1.14 worksheet. Let me know if there's questions on that. Bye.